In class on Monday, we talked about lines, and the solution that was presented in class used the y equals mx plus b form. So that's natural. We are trained from high school to think about the equation of a line as y equals mx plus b. But it turns out that that's not the best formula in most circumstances. Instead, we'd be really a lot better off if we would learn to use the point-slope form of a line. And so the idea here is we've got y, that's our dependent variable, and it's going to equal a number plus the slope times this x minus a. And that's what I want to focus on today. We want to think about this in a new way. So our first way to think about it is I'm just going to find the equation of a line and demonstrate how this process works. So we're going to find the equation of a line with a slope of a third, and it passes through a point 5,2. And remember the way that we talked about in class, to find an equation of a line like that, what we might do is, using y equals mx plus b, we would say, all right, we know the slope is a third, and so that tells me my equation is 1/3 x plus b. That's used the slope, so we've used our slope information, and now we use the point where we say, all right, I know x is 5 and y equals 2, and when I substitute those in, I get a formula that 5 equals 1/3 times 5, that's my x value, plus some unknown, and then I go finish solving for b. Let's see, I need a common denominator, so 5/3, 2 is the same as 6/3, so 6/3 is 5/3 plus b, and I discover my b is 1/3, and I have an equation of the line. My y is 1/3 x plus 1/3. So that's the y equals mx plus b form. The point slope equation, I just write it down. So let's clean this up a little bit here. So when I have a point, those are the coordinates of a and b. So I now know that a is 5 and b is 2. I know that my slope is a third, and y equals the point slope equation, I would say y equals my y value. So we're just taking the 2, we're adding the m times x minus my x value, and that's the 5, so x minus 5, and that's the equation. There's no solving. So y equals excuse me, y equals 2 plus a third times x minus 5. So we might want to ask the question, are these really the same? And we can see that the algebra works out. This is the answer, but if I wanted to see if they work out the same, I would distribute that a third. So 2 plus 1/3 x minus 5/3, and just as before, when I combine 2 minus 5/3, I get back the same formula that I had before. So I really like the point slope form of a line, because I don't have to go solve for anything, I just write it down. Now there's another reason I like the point slope formula of a line, and that has to do with accumulation. Accumulation is the idea that we start at a value and I'm adding a whole bunch of changes. I'm just gathering changes and recording them and keeping track of all my changes to get a final value. And the slope on a line gives us the rate of change, or the rate of accumulation. And a linear function, the ones we're used to from algebra, are functions that have a constant rate of accumulation or a constant rate of change. And so the slope is the rate of change, and for a line it's the same value for everything. So let's go back and let's look at another way of thinking about the point-slope formula. So this is my point-slope formula, except I've now written it as a function instead of y equals, so I've got f of x. So if I take f and evaluate it at a, when I substitute in x equals a, this x minus a gives me 0, and so I just get b. And so this is what we're going to call our initial point. This is our starting point, our initial position. When x equals a, the function returns a value of b. Okay? So how I can interpret the point-slope formula is that when I say f of x is b plus m times x minus a, the x minus a is measuring how far away is x from my initial x value, x minus a. I'm finding my delta x. And so when I multiply by my slope, I'm taking the delta x times the rise over the run, the rate of change, and that gives me the change in the output. And so my function is an initial value plus the total change. So it's, let me write that down. It's our initial value, and the m times x minus a represents an increment of change. And the delta x is how much x changes. The slope times delta x is how much the output changes, the delta y. Okay. So this is how I like to think about what a point-slope formula is doing. It's really powerful. We're going to generalize this instead of just being a constant b plus m times x minus a. Our goal is to understand how does this increment of change generalize for more complicated situations. To start thinking about what I mean by non-constant rate of change, I want to look at this example. So this example takes a rate of change and it considers a constant rate of change on intervals, but the constant value changes on different intervals. So we can see that my rate of change on this interval that goes from -2 to 1, that interval I have a rate of change of 3. On this interval that goes from 1, x equals 1 to x equals 3, I have a rate of change of -2. I have another interval that goes from 3 to 5, and my rate of change is going to be 4 on that interval. After 5, we have a rate of change of 0. Before -2, I have a rate of change of, of positive 1. So if I didn't know about all the changes, these constant rates of change mean that my accumulation function would be lines. So let's summarize that. So what we have is on each interval, so when I break up my domain into different intervals, on each of those intervals I have a constant rate of change, and so the function that measures accumulation is linear on each of those intervals. And if I think about what's happening on this first interval, when x is less than 2, so when x is less than 2, my slope is 1, and so I've got some function that we'll call a of x, our accumulation function, is some constant, we don't know what that is, plus 1 times x minus some value. I know the slope is 1. On the next interval, here from a -2 to positive 1, we have a slope of 3. So I fix that -2. On the interval from -2 to 1, I have a slope of 3. on the interval from 1 to 3, and x is between 1 and 3, I have a slope of -2 from 3 to 5. So for x between 3 and 5, I have a slope of 4, and for x bigger than 5, I have a slope of 0. And in the same way that I've written my function is some unknown constant, I don't know the points, but I know the slopes. And so I've got these lines that are, we know their slopes on the intervals, we just don't know what point they go through. Okay? So we'll talk about how we find those points on the next slide. All right, so we're given a piecewise continuous rate function. So we have this rate function. It can have breaks. We've got these jump discontinuities, but you can't have any infinite discontinuities. And here's the key thing. We didn't know how to get a point, so we have to be told somewhere we start. So if I have an initial point, and in this example we'll do my initial point says a of 2 is 3, we can create an accumulation function. And the key thing that we're going to use to find those lines is my accumulation is going to be continuous. All right, so for our example, we've already talked about what the slopes are, and let's think now about our initial value. We know that when x is 2, my function gives back 3. And so where are we? When x is 2, we're in this region where my slope, I know, is -2. So I have a point, and I have a slope from my rate formula, and I can write down the equation of my function valid on the interval going from 1 to 3. And now I can use point-slope form. I use the y value 3 plus the slope times the delta x, where the delta x is how far x is from 2. And this is valid for 1 less than x less than 3, so that's the interval from 1 to 3. And because we're continuous, I get to say that this is actually up to and including the endpoints. I can now use that to find the value of my function at x equals 3 and at x equals 1. At x equals 3, I can plug 3 into my formula. I get 3 minus 2 is 1, so I get 3 plus -2 is 1. That gives me a value at this point. And in a similar way, if I put x equals 1 into my formula, 1 minus 2, that's -1. -2 times -1 is +2, and so I get that a of 1 equals 5. A of 1 is 5. Now that I have two new points, I can use those to generate the point-slope formula for the next two intervals. For the interval that goes from 3 to 5, I'm going to start with this point at the left edge. A of 3 is 1, and I'll use the slope to find all the way up to 5. And for the interval to the left of 1, I'm going to use the interval with the slope of 3 and the point 5 to construct my formula. So I've used point-slope formula. For this point, I know that b is 1. That's my starting y value. So I have my starting value. My slope on the interval is 4 times how far x is from 3. So I measure how far x has changed, multiply it by 4, add 1, and I have the value of my function everywhere between 3 and 5. Similarly, I know at 1, x equals 1, I have a value of 5. So I use that point. I have a slope of 3 on the interval, and I multiply by the delta x measured around the point x equals 1. I have a formula. And now that I have those, I can use these two functions to find my a at 2 more points. I can find a of 5, plugging in 5 into the formula. So I have 2 times 4 is 8, 8 plus 1 is 9, so a of 5 is 9. and I can also calculate a of negative 2. A of negative 2, I'll use the formula that goes from negative 2 to 1. Plugging negative 2 in, I get negative 3 times 3 is negative 9, plus 5 is negative 4. And with those 2 points, I can calculate the formula for my function on the last intervals. I have point-slope formula. I have my starting value plus the change in x, the change in the function, which is the slope times delta x. And on the other end, I have an initial value of negative 4 plus the slope times delta x. And here, when I subtract negative values, I can think of that as plus, so x plus 2. And let's extend our bar down. And this is the formula. I've got the slopes that I wanted in each of the intervals. And by using the point-slope formula, I'm able to find the exact values that will make this function piece together continuously. I want to end this video by highlighting a geometric interpretation of what we've calculated, because this geometric idea is going to motivate and drive our definition and concept of the definite integral. Let's start by just writing down the values of our function at the points that we actually calculated. And so where were those points? I want to remind you that we started at x equals 2. We used the slope here of negative 2 to reach my endpoint at 3. And then we used the next interval going from 3 to 5, and we used that to calculate. Maybe I shouldn't be drawing these on the x-axis, but because it's not really the same function. But we used that to calculate it at 5, and then we did the same thing going backwards. We found a value at 1 and at negative 2. And so let me summarize a little table of the values that we calculated. Here's a table that summarizes the values we had just previous to this. We used it to find our formula for our accumulation function. And it all started with this initial value a of 2 equals 3. Right? So that is where we used a of 2 was equal to 3 when we found that first value. So how did I get this value at 1? Well, I started at x equals 2, and I went to x equals 3, and that corresponded to a change in x of 1, 3 minus 2. And if I take 3 minus 2, and I multiply it by this value of my accumulation rate, negative 2, and I multiply the width times the height, there's a little geometric figure. It's a rectangle, and what we call it signed area, delta x is 1, slope is negative 2. I'm adding this value. So this 1 came from my point-slope formula. I started at 3, and then I added negative 2 times delta x. And this is that area, the signed area of that block. Then what did I do? I went from 3 to 5, and that gave me a corresponding delta x when I did 5 minus 3 of 2. When I take that times this height of 4, I get another contribution of 2 times 4. And so I get a value here that it was my old value of 1 plus delta x, my slope is 4, my delta x is 2, that's where that came from. And if I even thought about where the 1 came from, it was the original value all the way back at 2 plus the first little block and the second block. Okay. So I had this negative area. That negative area came from this first rectangle. And then I add a positive area. That came from the second rectangle. Okay, so let's go left now. If I want to go left, going from 2 to 1, this figure, my delta x, went backwards. Oops, if I could write, -1. So my height is still -2, and so this 5 came from my initial value, plus my slope, times my delta x. And this time, my signed area is actually negative times negative is positive. That's where the 5 came from. And so I get a signed area that went backwards. Delta x was negative. And my last chunk that I'm going to add, I've got another increment, this delta x, going from right to left. It's negative, what are we at? -2 minus 1. This is a delta x of -3. Its height is 3, and so this block that we're adding is a slope of 3, a delta x of -3, so we're going to subtract 9. And that's where this -4 came from. It was 5 plus slope 3, delta x -3, and that's where 5 plus -9 gives me -4. There's this really nice geometric interpretation. What we're doing is we're adding signed area as we move our x along. So a point slope formula, I just have a constant rate. That slope times the delta x, it's always it's positive if I'm moving to the right, and the delta x is positive. I get these nice geometric figures.